Hello everyone. Today we'll learn about age detection logic, and these are the points that I will be discussing. Age detection logic is a circuit, a digital logic or a digital circuit that detects ages of square waves. See, this is a square wave and these are the ages, right? So this age detection logic, it detects both positive age and negative age. This is a digital filter. It can be FIR or it can be IIR. Okay. Input to a digital filter is the one is input samples and the second one is filter coefficients, and this is the digital output of this digital filter circuit. Okay. And let's say the sampling frequency of this input signal is 10 kilohertz. Sampling frequency here 10 kilohertz means every 100 microsecond we are getting one input samples. That means if this one is 0 microsecond, then the next sample will get our next samples at 100 microsecond. Then next samples will be at 200 microsecond. Okay. So this is what is the meaning of this sampling frequency. Then the filter coefficients, this f equal to this frequency is 100 megahertz, means this filter coefficient, it has been stored inside the system memory and the system works with this frequency, this 100 megahertz. This is a system clock. Okay. That means filter coefficient f equal to 100 megahertz means every 10 nanosecond we are retrieving this filter coefficients from the memory. That means we are reading this filter coefficients every 10 nanosecond. Okay. And this is the digital filter output, and this is the formula for this digital filter output, yn equal to xn into hn. So we are multiplying this input signal, the digital input signal, with this filter coefficients. Okay. And what is happening here, see, that means we are reading the filter coefficient. See, h, we are reading filter coefficients every 10 nanosecond, and we are reading this sampling frequency, sorry, we are reading this input signals every 100 microsecond. That means reading this filter coefficients is faster than reading this one, this input signal. See here, reading filter coefficient hn is faster than reading input signal xn, because here we are reading every 10 nanosecond, then we are sampling our input signal every 100 microsecond. And then what we are doing, then the output is yn equal to xn into hn. Then that means we are multiplying the first sample with the first one, the first filter coefficients. But what is happening here, because there is a frequency mismatch, because one signal is coming at 10 nanosecond and one signal we are getting at 100 microsecond, so there is a frequency mismatch. So we are getting the wrong result at the output because of this frequency mismatch. Okay. So what is the solution for this one? The first solution is either read this one hn or xn same frequency. That means if you are retrieving this your filter coefficient at 10 nanosecond, then you do this one 10 nanosecond, every 10 nanosecond you sample the input signal, or every 100 microsecond, because every 100 microsecond we are reading this input signal, so 100 microsecond we can read this filter coefficient. Okay. So these are the solution. So the solution here is retrieve filter coefficient, because the filter coefficient has been stored in the system memory and the system memory frequency is 10 megahertz. So what is the solution? Anyhow retrieve this filter coefficients, this hn, with respect to this frequency 10 megahertz. Okay, that means system clock. But do filter operation with respect to frequency equal to 10 kilohertz, because this xn frequency is, this input sampling frequency is 10 kilohertz. So unless and until we get these input signals, we should not do the filter operation. Here filter operation means yn equal to xn into hn. You retrieve the filter coefficient, but you do all the filter operation, that is yn equal to xn into hn, with respect to this frequency and not this system frequency. Because if we use system frequency for filter operation, then we are going to lose the data, right? So this can be done with the help of edge detection circuit. See, this is the coefficient frequency that we are retrieving, 100 megahertz. Then this is sampling frequency of your input signal, that is 10 kilohertz. This is the edge for this 100 megahertz signal. This is the edge for this one. So what we are doing here, see, whenever this input signal is sampled, at this edge this input signal is sampled, right? Then at this edge again input signal is sampled, then at this edge. So what we are doing, see, this is the same edge, this is the same edge, this is the same edge, this is the same edge. So with respect to this edge, what we have to do, we have to do all the filter operation. With respect to this one, this edge, we have to do all the filter operation. Why? Because at this edge we are reading the coefficient from the memory. At this frequency edge, at the edge of this one, again we are reading reading in the sense sampling our input signal. So if we do filter operation with respect to this edge, then we are not going to lose the data and we are going to get the correct output. So this is edge detection. We have to detect this edge, we have to detect this edge, we have to detect this edge. Okay, so this is the edge for this one. For first filter operation, this is the edge. For second filter operation, this is the edge. For third filter operation, this is the edge. For fourth, this is the edge. So this edge, these two edge we have to detect. That means we have to detect this input edge with respect to this 100 megahertz signal. We have to detect this one, this input signal with respect to this signal. We have to detect this edge with respect to this signal. Okay, so see what we have written here. Always at the red pause edge. Okay, I will explain this one again. Okay, so what is the circuit for this one? This is the rising edge. See, it can be rising edge or it can be falling edge. Okay, positive edge or negative edge. So it detects this rising edge signal detector. It detects edges of input signal and gives output equal to 1. So it is detecting the edges of this input signal, this input signal, this input signal, but with respect to this clock, this clock, this clock. Okay, this portion. Okay, so this is the circuit for this one. Okay, edge detection logic. So this is a D flip flop, this is my input, this is the clock, and this is the output. Then there is a inverter here. Okay, so this is the final circuit. Okay, let me explain how it works. So this is the clock, then there is some random input here. Okay, then we get this a. So here we are getting, because this is the first clock, so after this clock we get the output here. So this is the a, this is the what you call this properties of this flip flop. So we are getting this is the output of flop. Okay, flip flop, which is nothing but here input to this this inverter. Okay, so here we are getting this a. That means it is a delayed version of this input signal. Okay, because it takes one clock. Okay, then what is the output of this one? A naught is simply inverting this one. What is the whatever input we have, we are just simply inverting this one. Okay, so if it is 0, this will be 1. If it is 1, this will be 0. If it is 0, this will be 1. Okay, then what we are doing here, we are using an AND gate. Okay, so this is the input is being ANDed then with this one a naught. Okay, so this is the output. That means there is an AND gate in between these two. sorry, this input, this one, and this a naught. So 1 and 1 equal to 1, then 0 0 0 1 1 1. Okay, so see now what we did here, now we are able to detect the age of this input signal. See, here it is not the replication of the complete input signal, just the age here. This is the age, this is the age, so this age, we just wanted the age here, okay, not the whole signal. Okay, that means here this clock is, see, this is 100 megahertz, this is 10 kilohertz. So here this one is 100 megahertz, this frequency is 100 megahertz, and this input is nothing but this input, this 10 kilohertz signal. Okay, so this is a 10 kilohertz signal, this is a 10 kilohertz signal, and then this is the output. That means this output, this age we wanted. So anyhow we are getting here the with this logic we are able to detect this age with respect to this one. See, with respect to this one, then again the third one will be somewhere here, then with respect to this one we will get. Okay, so this is the explanation for this one. And falling edge, if you want falling edge circuit, this is the falling edge. Okay, the inverter is on the top, and the same, okay, same logic, circuit is also simple one. And if you want to write the verilog code for this one, then how we are going to write this one? Input your clock, this 10 kilohertz is your input clock, then you are detecting output, age detecting, this is E clock. Okay, you can give any name. Okay, then there is a range D clock. What we are doing here, see, E clock, the age detection, that means this logic, this one and this one. What we are doing here, output, we are simply input, this input, and with again this a naught signal. See here, the input is clock 10 kilohertz here. See, input is here 10 kilohertz we have taken here. Input is, we are ending this one with this a naught signal. Okay, so we are ending this one and here and with this inverter signal. What is this inverter signal is, we have taken a range variable. Okay, then D clock is the range variable, and then inversion of that one is not of D clock. Then this one will give you this age circuit. Okay, age detection, this one, this portion. Okay, then how to do this filter operation? Filter operation should be with respect to this system clock, that means 100 megahertz. So this clock is your 100 megahertz signal. So with respect to this clock only, with respect to this clock, whenever there is a edges of clock, whenever we get the edges of clock, then what we are doing, you read the coefficient and you do filter operation. Okay, first with respect to, see, always at the rate pulse edge of clock means with respect to 100 megahertz, already we saw here, with respect to this 100 megahertz only we are detecting this age. So whenever there is a age, here, age comes here, then you do the filter operation, Okay, so we are doing the filter operation when with respect to 100 megahertz, when there is a detection of this age, this is the logic, then you do filter operation after reading the coefficient. Okay, then we are not going to lose our data at the output side. Okay, and if you want to know about this D clock, how to declare this D clock, then you can write like this. Okay, always see, this D clock is nothing but, see, this is the D clock, right? This is the D clock. So this is nothing but your input signal only, the delayed version of the input signal, this part. So this is the D clock. Okay, so how to write this one in using verilog code, this D clock, it is just a delayed version of this input signal. So you can write like this, always at the rate pulse edge of clock, this clock is 100 megahertz. Okay, D clock equal to clock this one, that means clock 10 kilohertz. Okay, so this D clock is nothing but your input clock, that is 10 kilohertz. Okay, so this is all about your age detection circuit. I explained the theory part, then your circuit, and tried to explain this verilog code also. So if you have any doubt, then you can ask me on the comment section. And thank you so much for watching.